Welcome to the AE Canada East's first webinar of 2023. My name is Andrew Penner. I'm the president of the chapter here called Canada East. And I'm really pleased that our first webinar of the year is talking about something we haven't talked about yet on these webinars. Applications for reciprocating engines as distributed energy resources with some case studies in Ontario. Our presenter today is Thilo McAllister. He's an outspoken advocate for distributed energy resources. He's got an extensive experience and background in the energy sector, and he brings a bit of a unique perspective to the industry. He heads up marketing for TNT Power Group, and he's focused on discovering and developing innovative energy projects.
Thanks so much for the introduction and the opportunity to chat with the group here today. I prepared a lovely little conversation for discussion, and before we kind of dive into the material, I'd like to just kind of reiterate what Andrew said about questions. In my experience, having done lots of live presentations and virtual ones, the more questions, the better, and probably the more interesting the session will be for everybody. So if you get your questions in as we go, I've asked Andrew to just barge in and give them to me in the stream of presentation rather than just holding them all back until the end. And I think that maybe will lead to some more interesting dialogue. And I invite any and all of you to join in the conversation if there's something you'd like to know more about or add some perspective on yourselves. I think that would probably be great for everybody. So as far as what I've planned to cover today, in our scope of topic being about the applications for reciprocating engine generators specifically as distributed energy resources, here's what I plan to cover. So we'll chat a little bit about generators in general. I expect most of you are quite knowledgeable to a certain extent on that topic, but just a little baseline is useful. We'll discuss a little bit more, I guess you could say, about distributed energy resources and kind of, their proliferation and evolution in Ontario in particular, as we're seeing in other jurisdictions. And then I've selected a handful of case studies from real projects that we've completed in recent years that fall into this DER category. And then that will lead into a discussion of how we are working to decarbonize some of these generator applications using hydrogen as an alternative fuel. So that's what we plan to cover. As I said at the start, and Andrew mentioned, please get your questions in. And if we get a little off track or off course, I'm actually okay with that. I'd love to chit chat about what's most interesting to you. So to get started, I thought I'd just share a little bit about our kind of journey into the distributed energy world. Obviously, we're quite established in that business now with some very interesting projects that have garnered quite a bit of attention, particularly here in Ontario. But we've actually been around since the 80s with the generator business. The TNT in our name actually comes from truck and tractor. And that's because prior to the 80s, since about World War II, we were distributing John Deere tractors and trucks. So we've since pivoted and used some of those engines in and around 1980 to start making power generation units. And that led to our bread and butter. And we quickly retired the trucks and tractors and just focused on power generation. So now, we're all across Canada. We build generator systems custom in our own shop here for all sorts of applications, from like conventional standby power right through to CHP and peak shaving and prime power. And we've since added our own capacity for panel building and custom controls and switchgear and some controls integration work as well. That isn't really the focus of our chat today, but what I thought I'd kind of share is how we went from just doing the generators for the most common standby power applications to doing some very interesting things with them as distributed energy resources. So what is a generator? Well, in case you don't know, the simplest definition I could come up with is a device that's converting chemical energy in a fuel to electrical energy on a wire. And you need, a few components for this basically, but you need a fuel You need some kind of engine. In our case, we're using mostly reciprocating engines, but you can do it with a turbine as well, of course. And you need a generator, or what will sometimes be referred to as the alternator or the gen end of the device. And you put all that together the right way and you get electricity. There's a few more components involved, of course, that some of you would probably know. In some of my sessions, I leave all these blank and I do like a little game show to see how many we can actually label correctly. But given the format of this being a virtual webinar, I think we'll skip that today. But suffice it to say, there's a few more pieces in that puzzle, but it's actually pretty simple machinery that hasn't changed terribly much over, well, at least the last 3 or 4 decades. So one of the important considerations when you're building or selecting a generator set is the fuel type. And conventionally, of course, the most common fuels for generators are primarily diesel. And then based on your location and availability, we see natural gas becoming increasingly popular for power generation with these units, as well as propane if the natural gas isn't available. Each kind of have their advantages, right? So diesel is often favored because diesel engines have the fastest response time, up to at least around 800 kilowatts, with very, very good load acceptance. And at the larger sizes, they tend to have a smaller footprint or power density. So for standby power applications where you just need something to turn on when the lights go out, it's a classic solution and still favored by a lot of sites today. The challenges, of course, with diesel is that you require fuel delivery and storage, which adds some complexity and logistics and, a potential for things to go wrong. And you have to deal with the degradation of your fuel over time. It can become contaminated in many different ways and lead to a failure to start or some other problems with the engine. And of course, diesel is expensive and it's dirty. It's high emission, and it's increasingly expensive as time has gone on. And so that's one of the reasons we see a lot of favor to natural gas in the standby power market, not to mention continuous generators. The advantage there, of course, being that you don't require fuel storage on site if you have access to a pipeline connection, and you have a lower operating cost in terms of dollars per kilowatt hour of electricity. In general, they're quieter, and of course, compared to diesel, they're a lot cleaner on the emission side as well. They do struggle with load acceptance compared to a diesel engine, and the larger natural gas engines have to be built quite a bit bigger than the diesels because of the tolerances and the heat of combusting the natural gas. Pardon me. Excuse me. Propane is a great solution for standby generators when natural gas isn't available. So I know a lot of our attendees today are from eastern parts of Canada that don't necessarily have the natural gas infrastructure that we do have here in Ontario. Pardon me. And as a result, propane is a good solution because it has a lot of the same benefits of natural gas. And struggling a little bit with my throat this morning, apparently. But the propane does provide a lot of the same benefits of natural gas, maybe just not quite as much. And you do have the complexity of the fuel delivery and storage as well, similar to the diesel, although it's much easier to store than diesel because, it doesn't, if there's a leak or something, it doesn't run down into a creek bed or cause an environmental disaster the same way that a diesel does. Sticking with kind of this, our business came from this world of standby generators, right? These were the questions we're helping our customers answer the most. And the other piece of the puzzle when it comes to standby generators is some kind of transfer switch, right? Typically, you want a standby generator to supply power to a selection of the loads in a facility, and in some cases, the entire facility. So in a typical configuration, you'll have an automatic transfer switch that will sense the grid has failed and transfer your emergency loads over to the generator once the generator has powered up. And then when the grid stabilizes, the transfer switch will switch back over and reconnect all of your normal loads to the grid once again and continue business as usual. And typically these standby generators are firing up in less than 10 seconds, as is required by code in most cases. Sometimes, though, there's buildings that are more mission critical and choose to back up their entire load, in which case the ATS would connect all of the loads in the building to the generator during the power failure. And this is kind of, you can get really fancy with the different types of transfer switches with far as open and closed transitions, if you can tolerate, an interruption when it switches back to the grid, and some other fancier configurations. But, typical standby projects, probably most people in our group today are familiar with. I just thought I'd kind of show one for context. This is a typical problem we have to solve for standby power, where this is the University of Waterloo in Ontario, really close to where I live in Kitchener. And we have a 1 megawatt emergency load. And this is an outdoor installation, but it's on a campus. So like through that wall behind the generator is a lecture hall. And when these come on during an emergency, or when they come on for routine testing, obviously they have to be quite a bit quieter than you might require in an industrial area or in a remote location where the sound levels aren't a problem. So, for a project like this, we supply a couple of 500 kilowatt units with a sub-base fuel tank. So we have 24 hours of on-site fuel storage right there with the generator, a weatherproof enclosure. This one's a bit different though, because it was modified for the additional sound attenuation. And it's not particularly exciting, this type of project, but it's much needed because, facility managers in Canada are definitely paying more attention to extreme weather events and grid outages. We've had the misfortune to experience some long grid outages in Ontario and in other jurisdictions as well. And having that resiliency of a standby generator that can create electricity itself from its own fuel source for a long period of time, of course, is worth its weight in gold in an emergency. But, as we kind of grew our generator business, most of the systems that we're building were just for this standby power application. And, other than when they turn on for routine testing, maybe they're only getting used once or twice in an entire year. And so, this is really not a new technology. Generators have been used like this for decades. More recently, though, through the proliferation of distributed energy resources, or DERs as we like to call them, some organizations, at least the more savvy ones, have realized that maybe they're not asking enough of their standby power equipment, either in the design stage or as a retrofit option, and that generator sitting in its enclosure next to the building is maybe capable of providing a little more value to the system operators of our grid than it is just to them behind the meter. And so, with distributed energy resources and generators included, we have this opportunity that allows for the development of some new business models and revenue streams for energy customers. And the Ontario grid in particular is sort of evolving. And from a way of like a top-down distribution system that we're all familiar with to a more, two-way transaction of power and information between grid consumers and power generators and system operators. So really, what is a distributed resource? I think we probably should spend a moment on that. It's really, it's a broad definition, and there's some different opinions of where the line in the sand is, but really, it's a decentralized power generating unit located usually at or at least close to the point of electricity consumption. And as opposed to a large power generating set, a nuclear plant or a hydro installation that's generating a massive amount of power for a large number of customers, a DER is typically just serving one or maybe two customers in a small area.
Hey, Tilo, with this in mind, sorry, there's a question that's come up.
Sure.
So in the context of broadening the reach of these resources to be deployed in more than just backup power applications, have you started to see any movement with respect to the use of hydrogen?
Yeah, for sure. So, I'm glad that question has come up already. It certainly is something that I'm actually going to cover in the scope of our slides. So I might just deflect that question for a little bit, but I'm looking forward to chit-chatting about that because, as a kind of sneak preview, a lot of these generators that are running on natural gas right now have the capacity to run on at least a portion of hydrogen with very few or no changes to their hardware configuration and very little changes to their controls. So there are definitely opportunities to decarbonize these units, especially if they're going to be seeing more hours in their involvement, as a DER. But we'll more on that to come. So with these, DERs, just as a point of interest, sometimes they're connected to the electrical grid. Sometimes they operate independently from the grid. Sometimes they're able to do both. And one of the benefits of a distributed energy resource above and beyond potential cost savings is that they make our electrical system as a whole far more resilient. When you have centralized power generation and everybody else is just a consumer, if something happens to the transmission system, if something happens to the distribution system, as far as a catastrophic event or some unforeseen shutdown, everybody's stranded. But the more distributed energy resources we have that are capable of generating their own electricity in a microgrid, isolated from the grid during an emergency situation, the more resilient we are. And I think that is seen, these days with all the projects that are happening to, fortify community centers and YMCAs and things like that with robust power generating assets. So to kind of look at this as a big picture, right? A typical electrical grid is a top-down configuration, right? Where we have a transmission system that's connecting large-scale power generation assets like nuclear and, gas-fired plants and solar and wind farms through a transmission system to local distribution areas, where a local distribution system, or the DS section, as we see on this graphic, distributes that power to individual consumers on their network. And the distributed energy resource, or DER class, exists primarily behind the meter on the site of those customers' buildings and their facilities, even inside them or in the space adjacent to them. And this really is part of that transition, as I said, of allowing a two-way flow of electricity and information, and all of it being connected and managed to some extent by the system operators. So I just thought I'd share as well, the proliferation of distributed energy resources in Ontario here and their projected growth. This comes from an Ontario DER impact study done by ICF just a couple of years ago. And, you can see based on the different projection cases that there is expected to be, here we see just solar PV and energy storage assets and their projected growth all the way up to 2030. Even at the more modest cases, it's a pretty healthy curve, right? So this brings us to another question, are there different classes of distributed energy resources? And before we focus on generators, I'd like to chit chat just a little bit. I mean, we have a group of distributed energy resources that we could define as non-renewable. And these are typically, reciprocating engine gensets, turbine power generators that use conventional fossil fuel sources that we kind of mentioned already, like diesel, natural gas, propane. And you'll see, battery energy storage systems there in the non-renewable category. And this might raise a couple eyebrows, but don't worry, it's in the next category as well. And the reason being, of course, batteries, as far as their emissions, are just the same as whatever charges them. So if you're in Ontario with an emissions-free grid, your batteries are very, very green as from an emissions standpoint. And they never add emissions directly at the site. But if you're charging them with coal power, it doesn't necessarily make the energy clean, although it may be a more efficient or effective use of that energy. And then we have our renewable DERs, right? Including the obvious candidates like solar power, wind power. Generators are running exclusively on renewable natural gas that might come from a biodigester or a landfill and these kinds of things. Hydrogen fueled generators, which we'll chit chat a bit today. That's definitely a hot topic. And we can include battery energy storage systems here, provided that they're being charged from a renewable source of energy. And then there's the hybrid group, right? Which is often a microgrid combining some combination of these various distributed energy resource assets. So maybe you have a generator and some solar panels and a battery in combination in a microgrid at a site. And I think that is the largest area of growth, because a lot of these assets contribute different strengths and weaknesses as a DER and have different capabilities, and blending them together is often the way to unlock the highest rewards from any single one of them. And as these different distributed energy resource classes are kind of coming online and figuring out how to work together and provide value to each other, I think it's just sort of indicative of the emergence of the new electricity prosumer as a class of customer. Traditionally, electrical consumers are, there's only one place to get your electricity. It's through the meter, and you pay what it costs, and you don't really have any self-direction or control over the source of the electricity that you're using, and you have a limited ability to participate in various demand response programs that the utility companies and system operators may provide. Your engagement is limited to power, turning off certain devices strategically to reduce your demand during peak times and things like that, which have value but are sort of limited. And we've seen the emergence of prosumers, who are those that can have the ability to produce their own electricity on site using DERs and have a much more active participation in demand response programs of various types, and may even be able to operate completely independently of the electrical system in their own microgrid, and have absolute control over the source of electricity that they use. So I think that's kind of how I wanted to share the baseline picture of DERs in Ontario with a bit of a context from generators. And really what happened with us is we were building all these standby generators, and we still do. I mean, that's the largest volume of business that we do at TNT Power Group, is supplying standby gensets for all sorts of commercial and industrial applications. But our customers really were the ones who came to us and said, is there something more we can be doing with these generators, and using them as DERs? So I thought I'd put together some examples of really projects that changed the way we think about generators and power generation behind the meter, and hopefully will maybe be a point of interest for some of you as well who are working in this industry in some capacity or other. So the first application that we're going to chat about is about microgrids and grid replacement projects, where a customer has decided to replace some or all of their electricity demand from the grid with on-site generation. And I have a couple interesting examples of customers that have done that, including one that did choose a sizable load that did choose to ditch the grid completely in favor of generating their own power. I'll also show you an example of where reciprocating engines have served to relieve constrained capacity in a local area on the grid, by generating, again, some or all of their power on site because it was not available from the utility system in the short term. And then we'll chat a little bit about how these generators can be used for global adjustment mitigation, which is, truly a made in Ontario challenge. And for our friends from the East Coast and Atlantic provinces, maybe not the most relevant, but certainly an interesting discussion. And so we'll shift gears here now and look at a couple of these projects. And one concept I wanted to just touch on before we do is something we call spark spreads. So this is a big driver for investment in behind the meter generating assets, where the cost of electricity from the LDC, from the local distribution company, is actually higher than it is to generate your own power on site. And spark spreads come and go over time, but historically Ontario has had quite a significant spark spread, and that has led to a lot of investment in behind the meter generating assets. So that's one big driving factor for investment in DERs. Another one is power quality. So I thought I'd share a story about a manufacturer in Blenheim, Ontario, which is down near Lake Erie, where, this is a site that has a peak load of close to 4 megawatts. They're a foundry, so they make parts for the agricultural industry. And they were dealing with, power quality issues in a rural area on a rural distribution network that was causing great hardship in the plant, where basically, anytime there was little fluctuation in voltage or frequency on their supply, they'd been installing increasingly more technologically advanced equipment that was very sensitive to these problems, and they would have shutdowns on their production. And they have one of the largest gun drilling arrays in all of North America in this plant, and every time there was a little hiccup, all those drill bits would snap off inside their parts, and they would just lose so much money and production time dealing with that. The owner of this business was a little bit of a firecracker, an older Dutch gentleman. And, he could not find a solution to this problem by working with his LDC. So he, on his own accord, decided that he was going to build his own power plant and ditch the grid completely. And I was actually invited to speak about this project at the APRO conference a couple of years ago, because it raised a lot of eyebrows, because this was a large customer, about a 4 megawatt load, that just decided to cut the cord. Like a lot of us have cut the cord with our cable company and have Netflix and Amazon now, although somehow we're paying exactly what we were with cable by having all these different services. But we're not going to talk about that today. But in this case, someone actually cut the cord to the utility system. And so it was a very challenging project to us, because he was set on this idea of being his own island of production that was not dependent on the electrical grid whatsoever. So we had to design a 4 megawatt power plant, fueled by natural gas, which was the available fuel source there, that could follow his load in an islanded condition. And the biggest challenge was that he has a huge hydraulic press that during production hours turns on every 15 seconds, and there's a massive spike in demand and an inrush. And if you're familiar with the way reciprocating engine gensets work, they can do load following, but it's limited, right? How much load they can accept in a very short time without losing power quality and having a dip in frequency or voltage. So the way we designed this plant was with 8 roughly 500 kilowatt natural gas engines, so that, according to their production schedule, we maybe are only running several of these units to supply the load, and they're all controlled and operated together to share that load as needed. When there's, higher demand on them, they can ramp up and down, and maybe they're all working, but pretty much always we're able to have one down for routine maintenance or an unplanned shutdown without disrupting the operations in their production plant. But to solve the load following problem, we integrated a line of ultracapacitors that would be able to take the hit of that largest piece of machinery that made that massive spike every 15 seconds. So when that press comes on, the spike in demand is met by the ultracapacitors, and then once the spike is over, there's enough time for them to recharge the capacitors from the generator sets to supply that demand when it comes along again. So as a result, the generators are running much more steady, much more fuel efficiently, and maintenance efficiently as well, while the capacitors are doing a lot of the work that's going like that, right? Now, in this particular project, it's just power generation. So if you're familiar with, generator efficiencies, converting natural gas into useful electricity is actually not a very efficient process, right? Somewhere between 30 and 40% of the energy in the fuel actually ends up as usable electricity on your wire, and the rest is primarily lost as thermal energy, heat, right? And in the exhaust and in the coolant that goes to the radiator. So in this case, it's a foundry, so it's unfortunate, but they don't have a use for all of that waste heat on site, right? And I think that's a bit of a travesty. And if anybody knows someone that wants to build a greenhouse next door and use all this heat, I'm sure we could work something out to capture it. And that kind of brings us to our next application, where we're taking the efficiency of this system from somewhere around 35% up to 90% or more by capturing all that thermal energy. So we can put a heat exchanger on the hydronic coolant loop of the generator, and we can put a heat exchanger on the exhaust, and recover most of that energy as hot water or steam. And with recip generators, usually we're going for hot water. Andrew, I saw you unmuted. Do you want to jump
Yeah,
in?
well, I just wanted to ask a quick question on the previous example,
Mm-hmm.
the islanded example. Can you just speak a little bit to carbon footprint? Like, it just occurs. I think it occurs to me, and probably many people that are watching, that with while the islanding of the plant met a business objective,
Yep.
a very important one, it was probably very cost effective, obviously, for the owner. What does it say though to our attacking of our carbon challenge?
For sure. I mean, that's a valid question, and the direct answer, Andrew, is that it's not a win from a carbon perspective, right? It's unquestionable that if a large manufacturer like this is driven to the point where they ditch the grid and build a natural gas power plant in their backyard that's going to run 24/7 and none of the heat is recovered, that's not a good thing for the environment, right? In this case, I sympathize a little bit with the business owner because he was facing such a catastrophic power quality issue that he would either have to move his entire business somewhere else, because he couldn't get the upgrades to the utility system being at his location,
Mhm.
right? Or, just deal with the problem and the loss. So I think there are opportunities to decarbonize this plant with hydrogen, which we're going to talk a little bit about soon. But as it is right now, it's not great.
Mhm. Is when this project was constructed, you said you spoke about it a few years ago. So obviously the carbon tax probably didn't play a significant factor in the business case. Do you
Yep.
see a project like this needing to revisit the business decision in the next 2, 3, 4, 5 years as the carbon tax continues to escalate?
Yep. For sure. For sure it does. That pressure on the cost of fuel being the carbon tax and escalating annually will definitely need to be factored in. And you're right, when this project was designed, there was no carbon tax, right? One of the design considerations in this project that actually the customer had requested, one of the reasons we used 8 smaller units in addition to the load acceptance capabilities that they offered is so that, if the project changes and that needs to be reevaluated in the future, these engines can, quite easily be remarketed elsewhere and sold on the used market, because they're a 500 kilowatt continuous rated natural gas engine that's in very high demand. So if the business case no longer makes sense, it still does for now. But if the business case no longer makes sense at some point down the road, there is the flexibility to redeploy them for another application and recoup a lot of the investment cost in their kind of retained value.
That's awesome. Thanks.
Yeah. Yeah, no problem. So let's talk about making things a little greener, okay? So if we can use all that thermal energy, then it becomes a lot more environmentally friendly. And in fact, combined heat and power generation is the most environmentally friendly way to extract electricity from a fossil fuel like natural gas. It's still not as good as a solar panel or a wind farm, but it is better than a natural gas peaker plant on the 401 that's only running, certainly no more than 50% efficient. So if we can recover all that thermal energy from the generators that are running to create electricity anyways and put it to work as hot water or steam, then we can have a winning scenario and even improved economics as well. So I thought I'd show you one example of that where even on a smaller scale, the last project we looked at being 4 megawatts is quite large, but CHP projects can be quite small too. This is a 140 kilowatt unit that sits on the rooftop of a condo building in Toronto, and it runs 24/7. It's sized to the base load demand of the building so that we'll never be exporting any electricity to the grid, and that the generator can run at 100% of its capacity, its most efficient power band, 24/7, and supply electricity to the customer at a lower cost than they can buy it from the utility company. And then the heat is recovered from the exhaust and the coolant in the form of hot water, which is used to preheat the water that's going into their existing boiler system. And this project was a retrofit. So the unit is a skin tight enclosure. It's not a huge thing. It sits on the rooftop next to their mechanical penthouse. And the hot water goes right through the wall into their boiler system. And their boilers, actually, they were able to retire one of them, and the others have a much lower load because they're now getting their return loop from the building preheated into their system. And this one, just as an aside, was actually funded as a power purchase agreement, and it's something worth investigating if you're in the DER space and you're struggling with capital expenditure averse customers like condo boards. That sometimes, if there's a good economic case, like there was for this one, where it was a slam dunk financially for the customer, a company like ours can own and operate the system for a period of 10 to 15 years and just sell the electricity and the energy used by the customer at a contracted rate that provides them with an advantage over the status quo. And that's exactly how this was done. We've actually done 4 of these projects with GTA condominiums, where the generator just sits on the roof and operates within the baseline. And of course, the other benefit here, and this is something that's become more a part of the conversation in recent years, is the resiliency that is available from a CHP generator. Because if there's a power outage, a standby generator has to turn on. And it should be coming on routinely for regular checks and maintenance and stuff. But when you need something to turn on in a moment, there's always the chance that it won't. A CHP generator is already running 24/7. So in the event of a power failure, it can be islanded from the grid. There's different configurations for doing that, but it's business as usual for the CHP, and it can energize, your emergency loads or whatever you want to put on it. And from a resiliency standpoint, that's huge. And that's why we see CHPs at hospitals and, community centers and different disaster relief designated areas. CHP is a fantastic option. And for, apartment buildings and condos that want to maintain sustained occupancy during 3 days of power outage in the middle of an ice storm when it's really cold out, having a CHP generator on site connected to natural gas grid offers resiliency that pretty much nothing else can. So kind of, moving on to another use case for recip engines is when there's actually not enough capacity available in a local area. And I would expect some of you have probably heard about the shortages of electrical capacity in the kind of Windsor, Essex, Chatham area, particularly around Leamington, Kingsville, where all the greenhouses are. And this is due in part to the boom in construction of new greenhouse facilities and expansion of existing ones for the cannabis legalization some years ago. And just in general, vegetable growers are now adding lights to grow year round, and there's a huge spike in energy demand. In fact, it's expected to go from about 500 megawatts up to 2,100 megawatts in 2035. So there's lots of new transmission projects, coming online in the next few years. But the reality is that there's a lineup of customers who can't expand their business, who can't energize their loads because the capacity is simply not available at their service. And so in the meantime, we've seen a lot of growers look to combined heat and power generation to power their facilities. And this is a project we completed, I guess it was 2021, I think, was when we commissioned this, maybe 2022, forgive me. But basically, we had an existing grower, a tomato grower in this case, where they had a large facility growing tomatoes for, essentially 3 seasons of the year. And they had decided to build a new 6-acre range that would grow year round, state-of-the-art technology with high efficiency lighting and all the latest gadgets and doodads. And, they were constructing this facility and were not able to get the 2 megawatts of additional power capacity from the utility company to energize the facility. So they either had to scrap their plan to grow, they had to move it somewhere else in another jurisdiction that wouldn't, of course, be logistically feasible for them, or they had to generate their own power. So in this case, we supplied 2 highly efficient 1 megawatt CHP units that would supply 100% of the electricity required for the new greenhouse, islanded from the grid, so it's not interconnected to the grid at all. Lighting loads and greenhouse loads are great for CHP because they're quite level and steady. There's not a huge amount of variability, unlike that manufacturing project we just talked about. But basically, all the thermal energy is recovered from this site and dumped into their storage tank, which you can kind of see in the background there, and then used in the greenhouse as well. So it's a really cool project, and like greenhouses and CHP have been hand in hand for generations. The other opportunity here, although it was not an element of this particular project, is also to recover the CO2 from the emissions of the generator and use that CO2 in the greenhouse. A lot of greenhouses, some crops more than others, already generate CO2 with burners or truck it in to essentially fertilize their crops and increase the CO2 levels in their greenhouses. And when we have a generator running 24/7 right next to the greenhouse that's generating CO2, and we wish it wasn't, we can recover a lot of that CO2, further reducing the emissions of the project and provide it into the greenhouse the same way they would otherwise be doing with a burner, which would be the worst case, or maybe trucking it in from elsewhere if it had been recovered. And that's sort of another application that we've seen in local areas where, like, we've done this in the Niagara region as well, where the utility system exists, but there's just not enough capacity without doing a massive system-wide upgrade in a local area that isn't financially feasible. So businesses that want to move there or expand their operations need something like a generator to create the power on site. And then we have this thing in Ontario called the global adjustment. And, with respect to everybody's time today and the mix of our audience being from, areas outside of Ontario that don't have something called the global adjustment, I'm not going to do a deep dive into how global adjustment works, but I thought I would summarize it for you, okay? And I'll do this through a story of one of our largest GA mitigation projects, where we have a multinational manufacturing enterprise that's basically like, their plant is a small city, right? And they may or may not make cars, to give you some additional context. And, their peak loads are well in excess of 20 megawatts. So they have a sizable impact on the electricity system based on their activities in the plant. And they pay millions and millions and millions of dollars in global adjustment fees. So what is a global adjustment fee? If you're not familiar with it, basically in Ontario, there's a charge added to everybody's electricity bills, whether it's visible or not, that is used to pay for certain electricity system costs that aren't covered by the hourly Ontario energy price. So these includes like certain infrastructure upgrades and maintenance, different conservation programs, and some of the way our energy procurement is contracted with generators. So basically, there's something called the Industrial Conservation Initiative that allows large energy customers to opt into a group called Class A that allows them to get some relief from these global adjustment charges in return for reducing the peak demands of the province during coincident peaks. So this is a financial incentive to the largely manufacturing base that benefits from it, that allows them to be a little more competitive interjurisdictionally. Because, if you're paying 15, 16 cents per kilowatt hour of electricity, because you're not part of this initiative in Ontario, and your competitor, or you're looking at, a plant of that you own in another jurisdiction that pays less than half that, that's a huge difference in your cost of operation. And it's a serious problem that, could reduce investment in business in Ontario. So the system operators get the benefit of flattening the peak by sending a price signal to the largest customers to reduce their demand during peak times. And the large customers, of course, benefit from saving on their energy costs if they can provide that demand response. So Class A customers, like I said, I'm going to try not to dive into this too deeply, basically pay their global adjustment based on how much energy they use during the 5 highest peaks of the year. And they can predict these peaks in a number of ways. There's a free tool that the ISO provides, or there's lots of private consulting companies that will give you peak notifications when they predict these peaks might occur. But long story short, you kind of have 3 options if you want to curtail your load during a predicted peak time. You can shut your business off or turn off your biggest loads. You can discharge a battery on site, or you can energize your facility with a generator system, right? They each have kind of their own advantages and disadvantages. Obviously, the simplest is just to turn everything off. The challenge with that being, though, that you can't operate your business. And it's a 1-hour peak that you have to hit, but you don't know exactly when it's going to occur. So typically we see curtailment periods of 4 to 5 hours to make sure you don't miss the 1 hour that ends up being the peak. And so that pretty much means you're shutting down your business for half a day at least if you want to curtail manually. It doesn't cost you anything directly, but it certainly would cost you as far as your loss of operation and the impacts that might have. Using a battery is actually a really good solution and quite popular. And we do this for some of our customers as well, because it allows your business to continue without interruption. So, you won't even notice a difference when the battery is energizing your facility versus the grid. It'll be a seamless transition. And the challenge, of course, with batteries, I see a typo on there. There's a green check mark next to unlimited deployment window. Unfortunately, that is the drawback of the batteries, is that they do not have an unlimited deployment window. So frequently, you'll have a 2-hour discharge window. And if you want a 4-hour discharge window, it's going to be twice as expensive. So you do risk missing that 1-hour peak. And we have seen this with customers that install batteries, is that they miss a peak because they ran out of battery capacity before the peak actually ended up occurring. And you don't know until after the fact when the peak actually occurred. The other benefit of batteries, though, of course, is that they can, if they're configured correctly, provide emergency standby power for at least a short duration to the facility, which is a significant benefit as well. And generators really, from the simplest angle, I think are the easiest solution to this, because you can run them as long as you need to during a peak, and they're relatively cheaper compared to batteries. And you can also have standby power for your entire load whenever you need it outside of these peak shaving events. So we see them as quite popular. So back to our little customer, they chose to go with generators. And so we have an 18 megawatt power plant there now that turns on maybe 15 times a year, running for 6 or 7 hours each time, solely for the purpose of peak shaving this global adjustment charge. And then it has some additional revenues available through the demand response program and a couple of other services that it can provide to the ISO. But this system, so initially there was 12 units, and then based on the amount of money they were saving, it being so successful, we expanded the plant up to 22 separate containerized units for a total power output of about 18 megawatts. And this plant technically can run continuously, right? It has an unlimited deployment window. So as the peaks of global adjustment become more difficult to predict, kind of as a result of the success of the program itself, right? You now have all of your largest customers disappearing from the grid whenever it starts peaking. As a result, your peaks become a lot flatter, which is what the system operators want. But it makes it more difficult to predict when they're going to occur. So having the unlimited deployment window for your peak shaving generator system is a big value. The modular design here, again, allows for some flexibility. So we were easily able to add the additional units at the same location and just integrate them into the existing lineup. And, 5, 10, 15 years from now, if the project goals change considerably, they could be put on trucks and sold anywhere in North America or potentially further abroad without too much trouble, because they are highly reliable engines. So in this case, just to give you some ballpark numbers, these aren't for the sake of privacy exactly the numbers, but this plant has the capability of reducing global adjustment fees to the tune of over $5 million per year. And the operating cost as far as maintenance and fuel is well under $1 million. So they're netting just under $5 million in savings with an application like this. And so as you can imagine, with that amount of return available, this is something we've done for quite a lot of businesses across Ontario, not necessarily with 22 boxes, but 1 or 2 next to a facility, in a parking lot on a concrete pad or something like that. We have found plenty of applications for. There was a question about hydrogen earlier, and actually it was this customer that asked us that question for the first time about 6 months ago. And this is what they said. Because they're a large multinational manufacturing customer that is heavily invested in decarbonizing their operations around the globe. And it just so happens that this plant in Ontario wants to be a leader in that regard. And so they said, well, can we run this power plant on H2 instead of natural gas? And of course, we immediately said, yes, let's figure out how to do this. And we, with our partners at Guascor Energy that make these engines, and if you're not familiar with Guascor Energy, up until less than a year ago, they were called Siemens Energy gas engines, and then they're now Guascor Energy. You know, big corporations like to trade and swap large pieces of themselves to each other from time to time. But basically today, you know, what we learned from Guascor and from this is that with certain modifications, these existing rich burn natural gas engines are capable of burning a blend of natural gas with up to 50% volume of hydrogen with very little changes, right? So up to 15% hydrogen, we can use the existing natural gas engine configuration. We do a couple of adjustments to the ignition timing, and we don't need to derate the power output. So if this generator is putting out a megawatt on natural gas, it can put out a megawatt on natural gas with 15% hydrogen, but it will be a slightly lower overall efficiency, you know, just a few points. So maybe it was 37% efficient on natural gas, and it might go down to 34 or 35% efficiency when we blend in some hydrogen. Now, if we want to go up to 50% hydrogen, we do a couple of additional hardware changes to the same engines that can be done as a retrofit. 90 to 95% of the equipment will be unchanged, but we'll put in some different pistons, a different carburetor, a couple of component swaps like that, in addition to the controls changes. And we can now run on 50% hydrogen without derating the power. So we can still get a megawatt of electricity out of the same footprint, which is important for the goals of this project. So, you know, we explained this to our customer and said, well, you know, we can, without really any expense of significance, we can blend in 15% hydrogen right now. With a little bit of a retrofit, we can go up to 50%. And of course, their follow-up question was, well, what about 100%? What if we just do 100%? Can we do that right away? And because they, like I said, really want to be a leader on decarbonizing their operation. So our plan right now, and expected to be complete by the fall of 2023, is that we're going to be converting 2 of the 22 SR engines on site as a pilot project to run on 100% hydrogen starting the fall of 2023. And we're going to derate these. Their nominal output on natural gas is about 860 kilowatts of electrical power. We're going to derate them to be safe down to 535 kilowatts. And we're going to do some more extensive retrofits to these engines, including swapping out the turbochargers, pistons, some changes to the fuel system and compression ratios. But we're going to endurance test these units for up to 8,000 hours over the next year and see how they do. And we expect they're going to do pretty good, but that we'll learn a lot from the data. And right now, like I said, these engines are only running for peak shaving, but these 2 we're going to run continuously as a pilot study to learn about this. And then phase 2 of the project will be to apply that to the rest of the fleet to run it on 100% hydrogen without a derate, based on the learnings that we have from the 8,000 hours or so on our test engine. And while we're testing this one in Ontario, there's going to be a mirror image test happening at the manufacturing plant in Spain. They're actually a little bit ahead of us as far as developing the retrofits to the engine. So we are, you know, pretty excited about this project. And I think probably the question on everybody's minds looking at these earlier projects that I shared, like that manufacturer that's got a 4 megawatt power island that's just burning natural gas to power their operation without regard to the impact, you know, to a certain extent at least. It's projects like this and what we're going to learn from this that we can then use to apply to projects like that and decarbonize them. And with that, I've actually completed right on time, 9:59 a.m., the scope of what I had planned to share with you in an organized way. I want to say just before I hand it back to Andrew for any questions we may have in discussion, which maybe we'll carry on here for a few minutes, that if you have any questions about this, feel free to connect with me on LinkedIn or shoot me an email or give me a call. I'm always happy to chat, and I'd love to share a more detailed presentation with any group that might want it about any one of these projects or any one of these things that we cover. But anything related to power generators, switchgear controls, energy storage, we do it all in-house at TNT Power Group, and we'd love to be your partner. And thanks again for the opportunity to share some of our more interesting work from the last couple of years. And Andrew, I'll hand it over to you.
Yeah, well, I'm not gonna let you go quite yet. Excuse me, quite yet, because there are a few
Yep.
questions actually that have popped up, and I was looking for the right time to put them in, but they feel more kind of more broad in their scope. So I wanted to wait to the end to have a more
Yep.
kind of robust conversation about it. So a couple of questions are around how you integrate projects. So in the islanded example, you talked about capacitors being there to help even out the power coming out of the plant. And one of the participants was just asking, when you guys are looking at integrating these projects, are you looking at multiple technologies? And one of the examples was like a flywheel rotary based UPS. Would that have factored into your consideration, or like how does that work when you're building a project out?
That's a good question for sure. And I should disclose I'm not an electrical engineer by any scrape of the imagination. So I can speak to this stuff with a high level understanding, but not particularly deep. So as a once upon a time we had one solution and it was a generator. So when you have a hammer, everything's a nail. So every project we approached is, well, you could do that with a generator, and as we've evolved from just a generator company to really an energy solutions company that happens to make a lot of the equipment ourselves, or some component of the integration, we've had the luxury of becoming much more technology agnostic, right? So when there's a project like that manufacturing site, the customer really wanted generators for that one. So we didn't have any flexibility there, right? But when it came to solving the overall power quality problems, we certainly did. And I understand there was an evaluation process. I don't know specifically, what was on the pros and cons table for a flywheel versus ultra caps and what they offered, but of course we're going to go through that, and we don't do all that engineering in-house as well. Like we have a couple of partners that we'll work with and bring in as needed to be true experts to help us solve one particular problem in a larger scope.
Yeah, right on. So in the context of of the technology agnostic approach to integration, I can appreciate that there are many factors involved. It's not just equipment compatibility or fuel type or emissions or whatever. Like how do you guys balance out all of these priorities? Like, do you have a tool that looks at global adjustment versus other fees, emissions of one type of fuel to another when you're looking at what you're going to propose to your clients?
Yeah, I mean, I'd love if there's a tool for that. We'll buy it right away. That could actually balance all of those factors in a cohesive way. I think that the nature of the DER industry right now is that it's pretty new and it's evolving, and every single project that we sit down to consult a customer on is going to be different. So like, I can't really say there's a standard approach to those solutions, but for sure, like we have a more consultative approach to these opportunities where we really need to dig in and learn what are the actual problems the customer has, and then what can we apply from our other projects that we've learned already to solve them, and what do we need that's new that nobody's done yet, right? Like the hydrogen thing. I mean, every engine manufacturer on the planet right now is talking about hydrogen. Very few of them actually have a working hydrogen engine on a real customer location, not in a lab somewhere, right? So like having this opportunity to like bring that in and do it is exciting for us, but that didn't exist before we tried to do it. So to have a tool that could balance it all is challenging. I think, like I said, we do rely on some external experts to help us really model out the nuances of some of these things. In Ontario, the funding is so often, when I say funding, I should say the return, the revenue is not funding, is so dependent on the global adjustment fee because it's just so lucrative that the vast majority of distributed energy projects have some piece of that pie, worked into the equation, right? So that's big for us. And those are fairly easy to calculate out. And we do use a simple tool to sniff test combined heat and power project. If anybody wants to, it's on our website for free. If you go to our resources section at ttpowergroup.com, and it allows you to put in some simple inputs and just model out the economic snapshot of a CHP project with a 10-year cash flow report. So it'll tell you based on your fuel cost, based on your comparative cost of electricity, based on the size of the project and different values, the carbon tax or no, does this even make sense economically? If it can make sense financially, I hate to say it, but most of our customers are very pragmatic about this. It'd be great if they could cut their emissions, down to 20%, but if it costs too much, they're not going to do it, right? If we can save them some money and then reduce their emissions too, it's a much easier conversation.
Right. Well, I mean, that's a great segue to another question that I have, because you're talking about for the very first time ever, you've got somebody asking you about, in any significance anyways, about hydrogen, and being quite forthright about it. And it's, I mean, that's a pretty aggressive ask for a plant of that size to be converted to something never really done before, or done on at that capacity. But are you seeing, just in general in the marketplace, I know you have branch offices kind of throughout Canada, are you seeing a larger demand for the energy efficient, carbon reduced solution, or is that really still, like, has the carbon tax not really kicked people in the pants yet?
I mean, like, if this was the curve of people talking to us about it when they're talking about generators, starting, and let's start the curve in 2015, and there's no chatter, and there's no chatter, and there's no chatter, and then like in the last 2 years, I'd say it's gone like that.
Okay.
Right. I think it's going to go way up here.
Okay.
We're still, I don't know where we are on that S curve, right? But for sure the chatter is there. Like we get zany inquiries all the time about people who want to like power their Generac back porch generator on their deck with hydrogen and stuff like that. Can you guys help us do that? And it's like, well, we're definitely not there yet, right? But when it comes to just standby power, yeah, it's almost always part of the conversation when we're dealing with like a design build project is how can we manage our carbon footprint with this generator?
Right on. So, in that context, like when you're integrating a project and carbon is on the minds of your clients, are you also helping them navigate the potential credit implications? I think to the example, and somebody asked, the example of the greenhouse, where they needed capacity the grid wasn't able to provide, and there was an element of the project to extract some CO2 to pump it back into the greenhouses. Like, is that something that you guys help navigate, the credit bit?
Yeah, for sure. I mean, as far as like, I'd say we're the technology experts, not necessarily the policy experts. So we can definitely figure out how to put that CO2 into the greenhouse, and we can bring the right people to the conversation to help us navigate whatever credits may be available, right? And we have a general knowledge of these things and the opportunities that exist. But I would say that's probably not our personal expertise, right? We're more on the technology side and the solution side and the engineering side,
right,
than we are about dealing with the paperwork. One element that we do often take on ourselves, though, is like the connection impact assessments, which is a big part of these projects. Is how is this asset going to interact with the grid if it is going to, right, and all the paperwork and bureaucracy that's involved in making sure the correct relays and protections are in place and that kind of stuff. We certainly do. Sorry, I think I cut off your question, Andrew.
No, you didn't. I was just affirming kind of what you're saying, and what it occurs to me is that in engineering, it also takes a village. So it's you can't be by yourself and accomplish some of these integrated projects.
Yeah,
which it's good that you're able to point that out. The last question that's been posted, and something that I'm kind of curious about too, because anytime somebody starts talking about hydrogen, I get some anxiety, because there are many colors of hydrogen, of course, as some of us know, or many of us know, and some of those colors are not actually that decarbonized, in their entirety. So, of course, at the point use, you're not going to release any carbon, but certainly in the industrial process to create the hydrogen, there's a substantial amount of carbon. So, are you in the pilot that you're talking about? Are you looking at addressing some of the issues related to hydrogen supply, storage, reliability, source?
Yeah, that's a fair question. And actually, it's the same question we have with batteries too, right? Because you can have the battery, just like the hydrogen, is never going to create emissions when it's at the point of use, right? You can think of the hydrogen as a battery, right? It's charged by something. It's generated from something. So if you're generating hydrogen at a coal plant, it's like, well, not necessarily a win as directly as we might think, despite the fact how good everybody feels about using that hydrogen 1,000 kilometers away, right? So that's a really important question. For the scope of the pilot, I can't state how grateful we are to have a customer like this that's like championing this at significant cost to themselves, right? And they have actually taken under their scope the procurement and supply of the hydrogen, and on this particular project, and we're just going to take the hydrogen. So they're still evaluating. They have a number of different people bidding on that, but they are 100% trying to get it as green as possible, right? That is still feasible, right?
Yeah.
So that's a big part of the equation that we can't lose sight of, right? It's like, I feel like greenwashing is plague of the day for sure. And like, I'm really aware of it because I work for a generator company, and like, I don't want to give the impression that we're just trying to say generators are good for the environment, right? Like we're totally aware that when you burn fossil fuels, the negative outcomes that come from it, and we're trying to find ways to like still provide the solutions that our customers need. Like we'll always need standby emergency power. Like we always need a hospital to have its own power plant, right? You need these things no matter what. So how can we do them in a better way? And I think procuring the hydrogen is a big piece of that puzzle. And just like learning how, it's a bit of a chicken and an egg, to be honest, where you have the engine that's going to burn the hydrogen and turn it into electricity, and that technology is coming online now. From like, it's an arms race with the different manufacturers, right? But it's not totally certain that the hydrogen is available to actually, like, our customers tell us they want it, right? And we tell them, yeah, we're pretty sure we can do it right now up to 50%, no problem. And we're pretty sure we can do 100% with a little bit more testing. But will you actually have the hydrogen for us if we spend all this R&D, right? And so all the companies that are with the electrolyzers and the various technology to get the hydrogen, they're kind of doing the same thing, but they're wondering, is the market really going to be there once our technology comes online and we can provide it, at a reasonable cost? Is the market to buy this hydrogen actually going to be established? So, we're just going for it with this pilot project. And that's, I think, what has to happen is you just have to take the step, and hopefully the tech catches up.
Well, that's amazing, Tilo, and we're going to check back in with you in a couple of months, as
Cool.
that particular pilot rolls on, because I'm personally quite interested in to see how it transpires and what the outcomes are. Tilo, thanks very much for spending the time with us this morning. For those who stuck with us to the end, I hope you learned a little bit about distributed energy resources and their opportunities and potential. Thanks, Tilo.
Thanks, Andrew.